All right, in this video, we'll discuss section 5.7, which is analysis models for Newton's second law. And that means that it's a lot of problems. So we're not going to work down to number solutions. We're just going to set them up as some examples. So I have here, and some of these we've done in class, a lamp hanging from a chain or a rope or whatever, and at rest. So a hanging lamp. So if we look at the lamp, it has some mass m, and that results in a force of gravity acting on the lamp equal to m times g. And the chain or rope that holds it up has some tension in it, and it's at rest, so we know that these will be equal magnitude. All right. If we set up our motion equations here, we'll need to choose a coordinate system. I'm going to choose up as the positive y direction. So then we have a positive tension minus the force of gravity is equal to ma. But we're told that it's at rest, so 0 for our acceleration. We get that the tension is equal to the force of gravity. All right, the next case I want to look at is a box on the ground with a rope tied around it and a person pulling on it. And we're going to assume that this is frictionless because we haven't covered how to deal with friction yet. I think that's 5.8. We'll do that in the next video. So if we look at the free body diagram of the box, again, there's some force of gravity. This time it's in contact with the rope that the person has tied around with it, and the tension is in the direction that the rope is. And it's also in contact with the ground, so we have a force perpendicular to the ground, which is the normal force. I'll choose a standard coordinate axis again. And if we want to find our equations of motion for this case, well, we're going to need a sum of forces in the x and a sum of forces in the y direction. Both of those are going to be equal to the x and y component respectively of acceleration times the mass. All right, so in the y direction, we have normal force minus gravity equals 0. He's pulling horizontally on it. So in the x direction, we have, well, the only force in the x direction is tension, and it's in the positive x direction. So that's equal to ma in the x direction. Oh, and I did something here without justifying it. Why did I put a 0 here? Well, as this object were to move, I know that it's going to move along the surface of the ground. So there's no change in height, no change in our y coordinate. So my y acceleration is 0. That's what we have here. There are equations of motion for that case. The next case I want to consider, this video is just going to be case after case set up down to the equations. An object sitting on a surface. In the book, this example is a book with a hand, looks more like a foot. We'll just make it a foot. So somebody's stepping on the book and pushing it down on it. So if we look at a free body diagram here, what do we have? Okay, and the book is at rest. We have gravity, right? The book has mass, so there's a force of gravity on it. It's in contact with the ground, so we have a force perpendicular to the ground. Make it a little longer. We'll see why in a second. And we have somebody standing on it, right? So there's another contact surface. Well, that contact surface pushes the book down, right? So we have another normal force pushing down, and this is the force on the book due to the person standing on it. So we'll call it N1 from the ground and N2 from the foot. And in this case, well, this is a one-dimensional case again. I'm going to use up as the positive y direction. So we'll have normal force 1 minus normal force 2 because it's down, minus the force of gravity because it's down, equal to ma. But again, this is a case where a is equal to 0 because we were told it was at rest. So we get that the normal force from the ground is equal to the gravity plus the normal force from the foot, right? And this is very straightforward, but this is just another case of don't assume the normal force is equal to the weight. This is an example of that, right? The normal force here is not equal to the weight. It's equal to the weight of the book plus whatever force is pushing down on it with the foot. Next case, an object hanging kind of like the lamp in the first, but we're going to do a traffic light. And it hangs from multiple strings. All right. We have these on Lancaster that they replaced just a couple of years ago. And they have multiple lines to them to stabilize them in high wind. So in this case, I'm kind of exaggerating that the angles are different here. What coordinate system do we want to choose? We're free to use pretty much any coordinate system we want because it's at rest. So I'm just going to go with a standard coordinate system because I've drawn my angles to the horizontal and my gravity's in the vertical. So it's a convenient coordinate system. So now I need to break up my forces. We'll call this T1 for the string on the left and T2 for the string on the right. I need to break up my tensions into components. Looking at this, T1y is my opposite side, so that's going to be equal to T1 times sine theta 1. And T1x will be T1 cosine theta 1. Similar for T2, because we've defined theta from the horizontal. So the y is opposite and the x is adjacent. So we get T2y is T2 sine theta 2, and T2x is T2 cosine theta 2. All right, so now that we have our components, some people like to redraw this so that you only have components and you don't have the original vectors. So if we want to do that, we can. I tend not to. I tend to just go to the table at this point. But you could think of this as, let me use a different color for vectors on this so it doesn't get too crowded. Here's my gravity. Here's my T2x. Here's my T2y. Here's my T1x. And my T1y. So now we're at a case where we could take that and put it directly into our equations. If I look at my x direction, I can see that I've got T2x minus T1x equals 0. because it's at rest again, right? A equals 0. And if I look at the y direction, I can say T1y plus T2y, because they're both up, minus the force of gravity is equal to 0. Again, because it's at rest. So that's another way that we can do it instead of using a table like I tend to do. Okay, all of these we've used standard coordinate systems, so let's do one that isn't. The next one I've got a car sitting on a hill with some angle of incline. And you forgot to put it in park, right? So it's going to roll down the hill. So what does that mean? That means no friction, right? We're going to assume there's no friction, or it's very low, it's negligible. So if we look at a free body diagram for our car, we have the force of gravity is always straight down. That's what we're measuring against here, right? Is the horizontal. That's how we describe our angle of incline. But now our normal force is perpendicular to the surface that the car is on. So that's going to point out this way. And are there any other forces here? We said there was no friction. There aren't any ropes or anything. There's nothing else to give us any forces. So now we talk about our tilted coordinate axis, right? When we deal with an object on a ramp, or on a hill in this case, we generally use a tilted coordinate axis. I'll call it y prime and x prime. And this is because my rule of thumb is we know that the acceleration is going to be, let me do it in a different color because you don't put anything on a free body diagram that's not a force. So let me do it off to the side here. If we have any acceleration, it's down the ramp, right? So I like to choose one of my coordinate axes as the direction of acceleration. And that makes our equations easier because that means acceleration in the y direction is equal to 0 and acceleration in the x direction is equal to all of the acceleration, a. That means our y equation is going to be a lot simpler. And that's much better than having an x and y component of acceleration if we were to use a standard coordinate system. If we look at the geometry here, if I think about the vertical direction here that the gravity would be pointing in, well, this is the horizontal, so that makes a right triangle. That means this angle phi is complementary to theta, means they add up to 90 degrees. All right, but now if I look at my tilted coordinate axis that we know is perpendicular to the ramp, well, now that's a right angle. And that relationship that these add up to 90 because they're shared angles inside a right triangle, well, these two add up to 90 because they're shared angles inside a right angle. So that means this angle is also theta. And on our diagram here, that corresponds to this angle. So now we can figure out our components for x and y, for the gravity. I draw a right angle here, a right triangle here with sides parallel to my axes and the angle theta. Well, this is my FG in the y direction, and this is my FG in the x direction. And we now see that the y component is adjacent. So the y component of gravity is related to the cosine because it's adjacent. And the x component of gravity is related to the sine because it's the opposite side. So now that we've got our components taken care of, we're ready to make our equations of motion. And since I have non-trivial components this time, I'm going to go ahead and make a chart. So look at every force on your free body diagram. We have the normal force, which is entirely in the y direction. And we have the force of gravity, which has components in the X and components in the Y. So there is our component chart, and we can make our equations of motion from that. Like I said just before, this is an alternative to writing your components on a new free body diagram. I like to use the table usually. So if I look at the Y direction, we said that there's no acceleration in the Y direction, so I just have Fn, oops, I forgot my sign here, right? If I look at my diagram, the Y component of gravity is in the negative Y direction. So normal force, oops, still red. The normal force minus the Y component of gravity is equal to 0. And the only force I have in the X direction is the X component of gravity, and that's equal to ma. So there's our equations of motion for this case of the car on a hill with no friction. These are trivial right now, but when we introduce friction, then the Y direction is going to matter as well. What else do I have? We talked about the scale in an elevator in class, so I'm going to skip that and go to the Atwood machine. I have a video of me doing this with a physical object that you can watch. It consists of a pulley with a string run over it and a mass attached to each end. We'll call this M1 and M2. And we're going to assume what we call a perfect pulley, right? Massless and frictionless. So the pulley doesn't matter. All it does is turn our string. Okay, I've got two objects. I can't do this with one free body diagram. So if I look at mass 1, oops. I've got the force of gravity and I've got a tension. And if I look at mass 2, I've got a force of gravity and I've got a tension. All right, it's one string. So we know that T is the same. Also, since it's one string, we know that any change in position is the same. That means any velocity is the same, and any acceleration is the same. And notice I'm putting magnitudes on this because let's assume that M2 is bigger than M1. Then this is going to accelerate upward, and this is going to accelerate downward, and that's why I'm putting magnitudes on that stuff. So how do we solve this? Let's choose a coordinate system. Now here's where it gets tricky. I can choose the same coordinate system for each free body diagram, or I can choose a different one that'll be consistent. I'm going to choose my plus X direction in the way of the acceleration for both diagrams. So if I look at my free body diagram for mass 1, that means I get tension minus the force of gravity on mass 1 is equal to mass 1 times the acceleration. If I look at the free body diagram for 2, I call down the positive X direction. So that means I've got Fg2 minus the tension is equal to mass 2 times the acceleration. All right, but I've already said that the magnitudes of the accelerations are equal. So I'm just going to replace these with just A with no subscript because they're the same. So now I'm left with two equations, tension minus M1G is equal to M1A, right? Now I'm just replacing the force of gravity with M times G, and I'm keeping subscripts for the associated mass. From free body diagram 2, I get M2G minus tension is equal to M2A. And that would be our equations for this setup. All right, so since I did something weird with my coordinate systems, I want to go through it again, but with a standard coordinate system. So let's redraw our free body diagrams. And we're still saying that mass 2 is greater than mass 1. Same setup, but we're just not using a weird coordinate system this time. Let's use a standard coordinate system for both. So up is the positive y direction. What do our free body diagrams tell us in this one? All right, so this is the smaller mass, so I know it's going to accelerate up. And this is the heavier mass, so I know it's going to accelerate down. So if I look at my looking at my free body diagrams to make my motion equations here, up is my positive y direction, so I have T minus FG1 is equal to, this is up, so it's positive, M1A1. If I look at this one, I've got up is my positive direction, so I'm going to say T minus FG2 is equal to, all right, my acceleration's down in this case, so I have to have minus M2A2. And you see that we end up with the same equation, right? If we look at our first equation, it's identical. Our second equation, just all the signs are swapped. Instead of FG minus T equal to MA, I've got T minus FG equal to minus MA, right? So it's the same equation, just arriving at it in a different way. And again, the magnitude of A1 and A2 are the same. So these two equations can also be replaced with just A. You just have to be very careful on this one that you're either choosing consistent coordinate systems or you're keeping in mind which way things are actually accelerating. All right, I wanted to do another two-body problem, but a little more complicated. So this time, let's imagine we have a track with a cart on it. And a hanging weight off the edge of the table. So this is just like the Atwood's machine, except one of our objects isn't free hanging, right? So if we look at, I'll call the cart M1 and the hanging mass M2. So if we look at a free body diagram for M1, well, it has a tension because it's attached to the string, but that tension's now sideways. It's a cart with really nice wheels, so there's no friction. There is gravity though, and that's going to be down. And it's on a track now, so there's going to be something perpendicular to that track, keeping the gravity from accelerating it downward. And the hanging mass, it's not touching anything else, so that's all of our forces. The hanging mass has a tension. That's the same tension, because it's the same string again, and we're assuming that we have a perfect pulley. And we have the force of gravity acting on mass 2. So if we want to set up our equations for this, well, this is two-dimensional. We're going to need X and Y. And again, I'm going to choose my coordinate system in the direction of the acceleration, right? So this cart, if we release this, the cart's going to be dragged across the table. So the positive X is the direction of any acceleration. And that's good because we like one of our coordinates to be 0 if we can, and in this case, the y acceleration 0. And the hanging mass is going to fall. So I'm going to call down my positive x direction for the hanging mass. So if I now look at my equations of motion, the left free body diagram, the sum of forces in the y direction gives me the normal force minus the weight is equal to 0. And the sum of forces in the x direction gives me the tension is equal to m1 times A. And I'm going to magnitude here for the same reason I was before. My free body diagram on the right, I chose down as the positive direction because that's the direction of my acceleration. So I have Fg2 minus the tension is equal to m2A because that's the object we're talking about. So, all right, so we have these three equations. This one's not really useful for this setup because there's no friction. And we can solve for the acceleration using these equations if we were to know the masses. All right, and we could do this on a ramp as well. We could have a ramp with a cart on it and have a hanging mass down. And now we would take into account everything we did for the car on the hill, as well as everything we did for the Atwood's machine. And this is a really long video at this point, so I'm going to stop even though I could just keep going. These are a large number of setups, and while they don't include everything, they should include almost everything you need when you combine them.